Hi everybody, we've survived Module 1, so let's get fired up for Module 2. This module is all about kinematics, but more specifically graphing. So next module, Module 3, will be more about the problem-solving aspect of kinematics, so in both 1 and 2 dimensions, but this module is more about graphing. So for example, going from position time to velocity time to acceleration time graphs and vice versa. So let's get started. Okay, so just a quick note. So we'll be talking about displacement, velocity, acceleration. Obviously, now that we are in this enlightened state, we refer to those exclusively as vectors. However, sometimes we do just refer to, say, the magnitude of the x component of velocity, and we'll find that simplification more and more as we go on in the course. But remember, just for our own sake right now, that these are vector quantities. All the statements I'll make is for vectors in the x direction. So for example, displacement in x, vx, ax, but also note that this is completely applicable to the y direction. Okay, so don't, or the z direction or whatever direction you want. Okay, so this is not tied into x specifically. I just needed to choose one for the example. Okay, so let's start with just an overview of a position time graph, right? This should be old hat for you. You've done this before, but just a note of what we can get from a position time graph. So of course we can find the initial position, right? That's important. That's obviously just going to be the y-intercept of the position time graph. We can tell, is the object moving towards the origin? Is it moving away from the origin? How fast is it doing so? So we can figure out its velocity. Okay, because we can find it's both its direction and the magnitude of its speed, right? Or the magnitude of the velocity is the speed, right? We can also determine the sign of the acceleration from position time graph, and also determine, yes, if the object is speeding up or is it slowing down. Okay, so note that position time, we can only get the initial position from the position time graph. It doesn't show up anywhere on the velocity time graph. So that's a note that we'll have to make for later, because that's actually quite important. So of course, again, the y-intercept is the initial position. So in order to look and see if the object approaches the origin or moves away from it, we can kind of talk ourselves through it, and I highly recommend that you talk yourself through the position time graph as as time goes on. Okay, so for example, we start at -5 seconds, and then as time starts, we are heading towards the origin, right? As time goes on, we are getting our x coordinate is increasing, right? Up until this point, so it'll reach the origin, 0, and then keep going, right? So that's what we're seeing here. So it's going towards the origin, and then it goes past the origin up until here. All right, we'll talk about this in a second, but this is called a turning point. At that point, it does what you'd expect. It turns around and starts heading back towards the origin. Okay, so you can kind of use 2D for this to kind of visualize what's happening, right? You're kind of riding the position time graph like a roller coaster. Of course, this is not exactly what's happening, right? Because this is happening only in one direction, right? It's only doing this, it's not doing this. This only happens over time, right? Our fourth dimension. But it's a good way to talk yourself through the graph. So after we hit the origin again, and then we keep going past the origin in the negative x direction, right? Up until here, change our mind, turn around, go back towards the origin, and then past the origin. Okay, so talk yourself through your position time graph. Make sure you know what's going on in it, okay? Okay, so I've told you that you can find velocity from a position time graph. So there's a couple ways you can do this. So we can talk about the average velocity. So that's the average velocity between 2 points. So all we need to do there is find 2 points on our position time graph, connect them with a straight line, and then use slope, right, rise over run to calculate the velocity, right? Velocity is the rate of change of position, so it ends up being the slope of the position time graph. So between 2 points, T1 and T2, you just find the corresponding x values and then do rise over run. Okay, of course, this is just the magnitude in the x direction of the average velocity. If I wanted to get fancy, I could also find the instantaneous velocity. So that uses something that you should recognize, if not from calculus, from Sec 5 math. The slope, the instantaneous velocity is the slope of the line that's tangent to the curve, right? So we draw the straight line that touches the curve at that point exactly once. Okay, then we can find the slope of that line, and that is the instantaneous velocity at that point. Okay, if we were doing this using calculus, this would be essentially, we'd be talking about the derivative, right? But if you haven't taken calculus, no stress, you can just think about it as the slope of the tangent. Okay, so note that, for example, right here, the slope of the tangent is 0, right? It's a horizontal line. That means that the object stops, okay, and it changes direction. Okay, so we reached its, yeah, so basically slows down, stops, starts going, in this case, in the negative x direction. All right, so speaking of which, let's talk turning points. For some reason, my share has stopped. Let me reshare. Sorry about that. Your time is precious. All right, so zoomed in all weird. Okay, so now let's talk about turning points. So a turning point in a graph, if we just look at a graphical analysis, which again, I know that you've done in Sec 5, a turning point is a local minimum or a local maximum. So it changes direction at that point, right? It turns around, you'd expect that. So either the object is headed to the right and then it turns and starts going in the left direction, or vice versa. So at the point, like we just said, the slope is exactly 0, which means that the speed is 0, which means it stops at that point, okay? We can also say a little bit about the acceleration from a position time graph. So, and we can do that by looking at concavity, which you might have touched upon in the past. So if you have a graph that is concave up, or a smiley face like we do here, I know that that region of the graph has a positive acceleration, right? Positive, smiling. I also know that if there's a negative acceleration, the graph is going to be concave down. Okay, very, very important. Negative acceleration doesn't necessarily mean that it's slowing down, as you can see, right? In this first little chunk of the graph where it's concave down, we have regions where it's both slowing down and also speeding up. So we'll talk about that in a slide or two. If there's a change in concavity, so it's this pink triangle in this graph, note that the acceleration is 0 at that point. Okay, so speeding up or slowing down, we can tell from the position time graph. Okay, so remember, this is our point where our inflection point where we change concavity. So if acceleration and velocity have the same sign at any point, that means that the object is speeding up. If the acceleration and velocity have the opposite signs, so one's positive and one's negative, the object is slowing down. So for example, in this first part here, I know that the acceleration is negative, right, because of its concavity. But I also know that the velocity is positive, right? The slope all the way through this first part of the curve in red is positive. So I can tell from that that the object is slowing down, right? But you can also kind of, if you imagine drawing the line tangent to this curve at every point, you can see that the slope of that tangent is getting less and less steep as you go on. So that means that it's slowing down. Between this maximum here and the point of inflection, I have still a negative acceleration, but the velocity is also negative, right? The slope of that tangent is also negative. So between here and here, I know that it has to be speeding up because the signs are the same. So you can think about it that as though, if the signs are the same, they're working together, so it's speeding up. If the signs are opposite, they're working against each other, so that slows it down. Okay, let's move on. And I know that this is a lot of information, and we'll see some actual, applications and sample problems in class. And I know there's also some in your textbook, so please take a look at that. Okay, so from a velocity time graph, what can you say? I mean, obviously you can say the initial velocity, which is the y-intercept. You can tell, is the object moving towards or away from the origin? We can look at the acceleration. We can say, is the object speeding up, slowing down? Again, just like position time. We can look at a turning point for a velocity time graph, and also we can determine the displacement. How do we do that? Let's see. So this is maybe a new concept for a lot of you. And you might be fairly familiar with going from velocity time to acceleration time, right? Because it's just the slope. You're just making a plot of the slope. Going from velocity time to position time, though, is a little bit trickier. Or maybe not trickier, but it's a little bit more different. Okay, so to go from velocity time to position, I mean, first of all, you're going to need the initial position. Okay, that's very important because otherwise you don't know where to start. Then you can find the area between the curve here and the positive x-axis, or I mean, in this case, the x-axis is t, right? So you're looking for the area between the velocity time graph and the t-axis. So for example, between 0 and 2 seconds, my displacement, my delta x, is just going to be this pink area, right? So it's going to be 2 meters per second times 2 seconds is going to be 4 meters. So if you started at 0 meters, your initial position is being 0. After 2 seconds, you're going to be at 4 meters. Okay, so you can draw a graph that way. Okay, one thing that's very important is that the sign of the area matters. So, I mean, so this area is going to be 2 meters, right? 1/2 times the height, which is 2 meters per second, times the base, which is 2 seconds, right? The area here, the delta x, is actually going to be -2 meters because it's below the t-axis. Okay, so note that the sign in this case is very important. Okay, so that's area of the curve. If I wanted to do the acceleration time graph from velocity time, I could just find the slope, right? Like I just said. So for example, for between 0 and 2 seconds, it's a straight line. The velocity, the speed is constant. So I know that my acceleration is 0 meters per second squared. The slope between 2 and 6 seconds is -1 meters per second squared, right? Obviously, right here, the object is going to stop, right? That's where the velocity is equal to 0. So in our cases, if I asked you to find, position time, velocity time, acceleration time, the velocity time graphs are going to be just linear, okay, or addition of linear functions, okay, like in this case, right? There's 1 linear, 2, 3 linear functions on this graph, okay? I'm not going to give you anything more complicated because you need calculus in order to solve that. So it's all going to be fairly, it's going to be linear, okay? So finding that slope is going to always be a number. Or, I mean, it's going to be 0 or, some other number. Okay, so all you need to do, take the slope of the tangent and graph that Okay, so just a quick word on acceleration time graphs. Obviously, initial acceleration is something that you can read on it, the sign and magnitude of the acceleration, and also we can work backwards here, right? We can find the change in velocity just like we went from velocity to displacement, okay? So one thing is, like, I mean, you could find the slope of the acceleration time graph, and all the accelerations time graphs that I will give you, the slope will be 0, right? Changing acceleration does make things a little bit more complicated. The slope of the acceleration time graph is interesting, and it is, you know, something in physics, right? It's actually called jerk. So the rate of change of acceleration is jerk. I'm sure there's some jokes about that. So no, you can tell your jokes about that in the group chat. Okay, so to go from the acceleration time graph to the velocity time graph, we can, just like, right, the velocity time graph, we could find the area under the curve. So for example, between 0 and 2 seconds, my change in velocity, right, not just my velocity, it's got to be a change in velocity, is going to be 2 times 1, which is 2 meters per second. I didn't label my axis for some reason. It's not good. Okay, so between 2 and 3, obviously my change in velocity is going to be 0, right? And then here my change in velocity is going to be what? It's 3 times minus 2 is going to be minus 6 meters per second. So again, the sign of the area that you calculate is very important. So again, I've talked at you a lot, and looking at examples of this and practicing drawing these graphs, like going between the different graphs, getting another graph from a graph, is very, very important to practice and something that you will be tested on. So to summarize this asynchronous portion, if you want to go from position time to velocity, or velocity time to acceleration time, then you have to find the slope of that curve and plot it. To go from acceleration time to velocity time to position time, we are now finding the area under the curve of those graphs. Okay, so stay tuned. Definitely, you know, do your checkpoint, do some practicing, look at the practice problems that I posted, and then in class next week we'll look at some, we'll go thoroughly through some examples of, you know, going between these graphs and start practicing.